In many real-life applications of differential equations, we have to deal with systems of differential equations. In this section, I will show you how to solve certain systems of differential equations, and we will start with a review of the elimination method for systems of linear equations. So the first example asks us to solve the system of linear equations 3x plus 5y equals 6 and 2x minus y equals 17 using the elimination method. So what we do here is we take the two equations and then we multiply them by a suitable constant and then add or subtract the differential equations. So let's say that we want to eliminate the variable x. What we could do is multiply the top equation by 2, and we can then multiply the bottom equation by 3 so that the x's will have the same coefficient. Now, that will then be equal to 6x plus 10y equals 12. And then we have 6x minus 3y equals 51. And now what we can do is we can subtract these two equations from each other, and the 6x and the 6x cancels out. That becomes a 0. And then we have plus 10y minus 3. That gives us plus 13y. And then 12 minus 51 gives us negative 39. So our equation now is 13y equals negative 39. We divide by 13 on both sides, and then we get the answer y equals negative 3. To find x, we can substitute y equals negative 3 into any of these two equations. So let's substitute it actually in the original equation. 3x plus 5y equals 6. So we take our original equation, 3x plus 5y equals 6. And then we get 3x plus 5 times negative 3 equals 6. And so 3x minus 15 equals 6. So 3x equals 21, and then x equals 7. So our final solution to this system of equations is x equals 7, y equals negative 3. Now, we're going to talk about differential operators. Hopefully you recall from calculus that an alternative way of writing dt of y, or dy dt, is capital D of y. In other words, we represent differentiation, in this case with respect to t, by a differential operator capital D. This lets us rewrite a differential equation like y double prime plus 4y prime plus 3y equals 0 as follows. So the second derivative is the derivative of the derivative. So we can write this as d of y. And then plus 4 times d of y plus 3y. And that equals 0. Now, we can use a shorthand notation d of d. We can write d squared of y plus 4 times d of y plus 3 times y equals 0. And we can basically factor out a y here. It's not really factoring out, but an alternate way of writing this is d squared plus 4d plus 3, and write that as a new differential operator that acts on y, and that is equal to 0. So we've adopted the convention that the operator product d times d is interpreted as the composition of d with itself when it operates on functions. So d squared, we interpret that as d operating on d of y. Now, let's see whether or not that makes sense. So we're going to try to show that the multiplication here is the same as this differential operator here. So let's take a look at what does d plus 1 acting on d plus 3 acting on y do. So we'll write this out. This is d plus 1 acting on d plus 3 acting on y. Now, d plus 3 acting on y, we can rewrite that as dy is y prime, and then 3 times y, so this is y prime plus 3y. Okay, and now d plus 1 acting on y prime plus 3y, that's the same as d acting on y prime plus 3y plus 1 times y prime plus 3y. And then d acting on y prime, that becomes y double prime. The derivative of 3y, that's plus 3y prime. And then plus y prime plus 3y. We can then combine the y primes here, and we get that y double prime plus 4y prime plus 3y is another way of writing this differential operator. But in shorthand notation, that's the second derivative. We can write that as d squared plus 4 times the derivative plus 3 acting on y. And we will see the significance of this in the next video.